Hi everyone, welcome back. In this video, I'll show you how I make a smart outlet that can be programmed to perform customized functions for controlling the power of my soldering tools. I recently reviewed this budget desoldering iron, and I was really impressed with its performance. However, it has no built-in switch, so I had to unplug it every time I wanted to turn it off. To make it more convenient to use, I was recommended to use it with a switched outlet. However, this is not always possible. To solve this problem, I designed a custom smart outlet that can be controlled remotely. It also has a timer that will notify you when the tool is warmed up and ready to use. When the first outlet is turned on, the LED will flash indicating that the tool is in warming up. After 3 minutes, the buzzer will sound 4 times and the LED will stay on, indicating that the tool is ready to use, as well as a notification if you leave it on for too long. All of these settings can be customized to meet your needs. In addition, there's a second outlet for the hot air gun, which needs to be cooled down before the power can be turned off. In addition to controlling the device through RF remote control, or using buttons on the cover, it also offers the option to control it via the Home Assistant via a Wi-Fi network. However, I prefer using the RF remote control, as it allows me to remotely control devices, without the need to access my phone or computer. Furthermore, all the necessary functions are already built into the firmware, so it doesn't need additional scripts in Home Assistant. This allows the device to operate with all its features even when there is no Wi-Fi network available. By the way, I've previously created a desk lamp with RF and Wi-Fi control, and I'll be using the same remote control for this smart outlet. If you're interested, you can check out the video for that project. And if you're into DIY and enjoy making things, you can subscribe to my channel to get an update on new and unique DIY ideas. So for now, let's make it. Starting with the main controller board. I use a 3 by 7 cm double-sided perf board. The board consists of 10 rows and 24 columns. I use my jigsaw table to trim it down to 20 columns. In the 3D printed part, I've included additional holes for mounting the PCB. Use 2 mm drill bit to drill a hole on the top right of the board, because the final wiring was turning out to be messier than I expected. Due to this, the middle hole might end up being obstructed by the wires, so it won't be necessary to drill that particular hole. Next, we'll proceed to attach all the parts to the board, and establish the necessary connections according to the provided schematic. I've included a link to the schematic in the video description below. To confirm that all the parts fit correctly, I recommended placing all the components on the board, and marking their positions before starting the soldering. For the microprocessor, I use this D1 Mini development board. It's one of my favorites because of its compact size and plenty of GPIO pins. Because of its great popularity, there are a lot of libraries and tutorials available, making it easy to implement, and find online assistance when needed. To connect the D1 Mini to the perf board, I use the female pin headers that came with it. This is my preferred choice when there is sufficient space within the enclosure. It provides convenience for future maintenance. I can easily detach the MCU board in case it needs a replacement, or the need for firmware flashing by connecting it to a computer. Once you are satisfied with the layout of all the components, we can proceed with soldering. In general, I prefer to begin with the smallest and flattest components, and then work up to the larger components. This will keep the board flat and stable during soldering. I'll begin with the resistor. For the components with long leads like this one, you can bend the lead on the opposite side to keep it in place. In some situations, I find it convenient to use the lead to connect to another component it needs to be linked to. Although I'm uncertain if this is the standard method, I've personally found it to be easier compared to creating a solder bridge. I recommended to initially solder only 1 or 2 legs of each component, just to hold them in place. This allows easier adjustments, if there are any issues that may arise. Additional solder can be added later when making the connections. Continue with the remaining components according to the layout. When attaching the female pin connectors for the MCU board, I recommend temporarily mounting them to the MCU board during the soldering process. This will ensure that the pin headers are aligned vertically to the perf board, and maintain accurate spacing. I also use a female pin header to connect to the RF module, so it can be easily to replace. I use a female pin header strip I got from Aliexpress. Since the RF module has 7 pins, so we'll need to cut the pin header strip to the appropriate size. First, just use a plier to pull out the metal pin from the desired hole. Then use a utility knife or cutting plier to cut it off. Finally, use a utility knife to trim off the excess plastic and smooth the edge with metal files or sanding paper. To use the RF remote control, I use this 4 channels RF receiver module. It's quite easy to use with the built-in learning feature, so no need for an extra process to obtain the remote control codes for programming. However, the application will be limited to 4 channels, and not allow individual programming of each button. During the pairing process, the module automatically assigns each button's signal from the remote control to one of the output channels, and the assignments may not follow a sequential order. Therefore, before connecting the module to the MCU, it's necessary to identify the specific output pin corresponding to each button you wish to use. While it has no issues using it with 4-button remote control, but when I try to use it with my 8 buttons controller, some buttons were skipped. Luckily, I need only 2 buttons for this project. With 4 buttons controller, I can use the other 2 with my LED lamp. So, for this project, I just stick with the RX 480 module. To use the module, simply connect it to your circuit like a regular switch. When the module receives a signal from the paired remote control, it will transmit an input voltage to the corresponding output pin. This will cause the MCU to register a high state. The output pins on the module are labeled D0 to D3, along with an additional VT pin. To identify the output pin, just connect the RF module to a breadboard and provide it with a 3.3 volt or 5 volt power supply. Begin by pairing the RF module with the remote control you intend to use. For this project, we will use the remote control in momentary mode. So press the button on the module once, and the LED on the module will stay on. Now press any button on the remote control. The LED will blink and goes off, showing that the remote is successfully paired. Now, you can determine the output pin corresponding to each button by using a multimeter. Start by connecting the black probe of the multimeter to the ground. With the multimeter set to measure voltage, use the red probe to test the voltage from each output pin individually. Then press and hold the remote control button you like to use. The output pin corresponding with the currently pressed button should read a similar voltage as the input power supply. I've connected the red probe to pin D1. When I press button C, the voltmeter read around 4.9 volts. This means button C is linked to pin D1. The VT pin works the same way. It will output whenever the module receives matched RF signal. This pin can be used to generate a notification when the module has received data. Once you have completed attaching all the components, it's time to establish the connections. I typically start by making connections that can be made using the component leads. Then I will use 24 AWG wires for the remaining connections. I prefer to begin with the connection from the DC input, which often branches out to multiple components. Once all the power connections are in place, you can proceed to establish the GPIO connections as per the schematic. Now, let's move on to the second PCB that will be attached to the enclosure cover. This PCB is where we house momentary switches for manual operation, and LEDs to display the module status. I use a 2 by 8 cm double-side perf board, and cut it down to 14 columns. After attaching all the components and connecting them according to the schematic, we need to solder wires to link them to the main PCB. I will use 5 pins JST-XH connector for the connection. Once the wiring is complete, now it is time to connect it to the connector housing. Gather all the wires together, and secure them with a cable tie to keep them organized. Cut all the wires to the same length, and use a crimping tool to crimp the header onto each wire. Pay attention to the alignment and orientation of each header, to prevent excessive twisting of the wires when they are mounted in the housing. Now, insert the crimped headers into the housing in the specified order, aligning them with the wiring arrangement on the main PCB. It is important to make sure that the ground connection is correct. However, if you make a mistake on other wires, you can always change the GPIO pin assignment for each component later while coding. Next, we need to prepare a wire for the relay module. The relay module I have already comes with a male pin header. To make things easier, I will use a DuPont style connector on both ends of the wire. I will connect the wire to a 4-pin ribbon cable that I got for a stepper motor. Simply use a crimping tool to crimp all the wires to the header. Again, pay attention to the header orientation before crimping, to prevent the wire from twisting. For this type of connector, be careful not to apply too much pressure to the insulator, as this could cause the contact to bend, and make it difficult to insert into the shell. Insert the contact into the shell, and push it until it clicks. The latch should be flush against the shell when viewed from the side. In my case, I'm using a wire that is a bit larger than the connector spec, so it requires a little more effort to insert. However, if you are using a wire that is the correct size, it should snap into the shell nicely. Before proceeding further, it's a good idea to flash the firmware to the ESP board, and test it to ensure everything is functioning correctly. To integrate the device with Home Assistant, and enable control over Wi-Fi, I'll be using the ESPHome Firmware. There are tons of tutorials about installing and using Home Assistant with ESPHome, so I won't dive into the details here. First, add a new device to ESPHome. Fill up a new name for your device. Then select ESP8266. Once the new device is added, click Skip. Next, edit the newly created device, and paste the provided source code at the end of the file. I've included a link to the code in the video description. In the ESP8266 section, change the board setting to D1_mini. To call an ESPHome script from Home Assistant, you'll need to add additional lines in the API section. After making the necessary changes, click Save, and then select Install. Choose the manual download option, and download the firmware in the modern format. Wait for the compilation process to finish, which might take a little while. Once it's done, the bin file will be automatically downloaded to your computer. Connect the ESP board to your computer. Go to the ESPHome web install page. Click Connect and select the appropriate serial port. Once the device is properly connected, click Install. Click Choose File, and select the downloaded bin file. And click Install. Wait for the flashing process to complete. And once the device finishes rebooting, it should be detected in Home Assistant. You can now proceed with configuring the new device and adding buttons to the dashboard. For the outlet that has the delay turned off, that is controlled with the ESPHome script, it needs a little tweak to make it function properly in Home Assistant. Create a new button card. Instead of using the relay switch entity as usual, I will use an LED entity. This will display the status of the corresponding LED, rather than the relay switch status. Next, in the Tap Action section, select Call Service, and choose the ESPHome API that we previously added. This will enable toggling the outlet when the button is tapped. As well as in the Hold action, select Call Service, then select the Force Turn-Off script. This will let you press and hold the button to turn off the outlet without delay. Once you press the button, the icon will change to amber, indicating that the outlet is now on. When you tap to turn it off, the icon will start blinking, indicating that the outlet is in the process of turning off. And if you prefer to force an immediate turn off, simply tap and hold the button. To test your circuit, connect the RF module, the front PCB, and the relay to the main PCB. Pay attention when plug in the relay connector, as it can be connected in both directions. Ensure that the ground pin is properly connected to the V- pin on the relay. Once everything is properly connected, supply a 5-volt power source to the circuit. Now, let's test all the buttons, LEDs, and the RF remote control to ensure they are functioning properly. If everything is working as expected, it's time to proceed with assembling all the components into the case and cover. I like to mention that the enclosure shown in the video is the initial version. I made some adjustments to a particular detail that I discovered after printing it. So, the STL file in the link will be slightly different. Let's begin by mounting the main PCB. First, I'll attach a razor to the back and secure them with M2 self-tap screws. I just added this razor after realizing that there was a need for more space beneath the PCB. Next, we will mount the relay using M2.5 screws. To make the installation easier, I recommended using a tap bit to create a thread before actually installing the screws. Now, let's move on to the DC power supply. I've used this compact AC to DC converter. It provides a 5-volt output, with a capacity of 700 mA. Solder wires to both the input and output terminals. Insert the power supply into the provided block. and then attach the cover. Secure the cover in place using an M3 by 15 mm screw. Connect the DC output from the power supply to the screw terminal of the main PCB. Next, attach the RF module to the pin connector. Finally, attach the D1 Mini to the board. To manage the main input, I use a 2-inch 4-out quick connect terminal block to split the input to both the relay module and a 5-volt power supply. Since I salvaged the power supply from another project, and the wires turned out to be too short, I will need an additional screw terminal block to extend the wiring. Connect live wires from the terminal block to both COM terminals on the relay module. Then, connect the live and neutral wires to the power supply. Moving on to the front cover. Begin by mounting the outlet to the cover using M4 screws. Inserting M4 nuts into the provided slots on the bottom of the cover. The slots are designed to snugly fit. Simply align the nut with the hole and tighten the screw, allowing the nut to securely fit into place. Insert button caps to the cover and mount the front PCB to the front cover with M2 self-tap screws. Make sure that both button caps can move smoothly and without any obstruction when they are pressed. For the main input wire, I'll use a 2x1 square millimeter VCT wire, which has a diameter of approximately 7 mm. On one end, I've connected it to a folding AC plug. Connect the other end of the wire to the quick connect terminal block. Make sure it's securely fastened. To keep things in place, use some M3 screws to secure the quick connect terminal block to the enclosure. Lastly, secure the main wire to the enclosure using a cable clamp. Now we've successfully attached all the components. It's time to attach the cover to the enclosure. Refer to the provided diagram to properly connect the AC wires. Let's start by connecting the neutral wire to the quick connect terminal. Next, we need to connect both live wires from the outlet to the normally open terminal on the relay module. Connect a wire from each socket to the corresponding channel of the relay. Finally, connect the wires from the front PCB to the JST socket on the main PCB. Now we can close the cover. I've provided holes for M4 hot melt insert nut. But for now, I'll just use M4 screws. The AC socket I've used is a standard wall mount socket commonly found in my region. However, it may not be as popular in other regions. So I've included an alternative cover that can be used with this universal AC socket. Additionally, there are newer solderless versions available with a thinner profile, which provides more space for the wiring underneath the outlet. Anyway, please note that I have not tested either of these options yet. Alright, that's about it for this project. In the description, you'll find links to all the 3D print parts, and a list of materials used for this project. If you have any questions, feel free to leave them in the comments below. If you found this video helpful, I'd really appreciate it if you could give it a thumbs up, and consider subscribing to our channel. I'll be sharing more awesome DIY ideas and projects in the future. Until next time, take care, and thanks for watching.